So welcome back. We are looking at 1.6 transformations of functions. I'm going to warn everybody that this section has a lot to it. There's a lot that's going on here. There's definitely going to be a lot of graphing. We'll be working with parent functions, so functions that we've seen previously, so dealing with linear equations a little bit, but not too much. Some parabolas, so dealing with terms like x squared or vertex form, which you should have seen in Algebra 2. We might also see some cubic functions going up, pausing for a moment, and then continuing in that fashion. And we'll also be seeing some square root functions. We'll be using Desmos for this. We'll be graphing. We'll be seeing how some of these equations change given select modifications with constants towards the front or in the middle of the function or in and around. So we'll definitely be recognizing a lot of common functions, so ones that we've seen before, like the ones up here, using vertical shifts to graph functions. So occasionally we'll see how some equations will be in their normal format, but occasionally we have to move all of those points up 1 unit so that it looks as if it's a little bit higher up. We'll see some horizontal shifts, so some of the graphs might have to move to the left or to the right so that we know where they're heading. Some reflections where if we have an equation graphed out, we might need to see this reflected over the x-axis like so, occasionally over the y-axis. We'll get to that. Vertical stretching and shrinking, more so with quadratics and cubic functions, and also horizontal stretching and shrinking. So with this particular video, we're only going to be going over the types of transformations that can happen, starting off first with the horizontal shift. So I've decided to make this a little bit easier using these two ways of remembering horizontal shifts and vertical shifts for linear functions or quadratics or cubic functions, where if there's an h representing the horizontal type of shift, this is going to be on the inside. So we'll see first this high part. So we're saying high to the terms that are inside. So the horizontals on the inside. If we see a term is being added, that is going to be shifting the original parent function to the left, that number of units. So if we had something like x squared, and we were shifting, let's say that we're adding on 3 units inside parentheses, how do you think this would affect the original graph? So you should be saying that with this function, we would be shifting the original parent function, x squared, 3 units to the left. We say parent functions like x squared because we've seen those before. And a lot of this section is going to kind of be a before and after. So if you were wondering what was up with the Squidward picture towards the front, we'll see some original parent functions, how we know some of the equations, and see potentially a more chiseled out version or a shrunken version or a version that's flipped over. So a lot of this is going to be comparing what we've seen previously using these horizontal shifts and vertical shifts. For the second option, you might notice that in here we're subtracting a certain number of units, and this would imply that we're moving to the right 3 however many units. So if we had here x and we're now deducting inside parentheses, this would be moving 3 units to the right. So notice I don't have too many visuals here. I'm just kind of explaining how this would work with some equations. Eventually we'll see the graphing and that'll make a little bit more sense. We then hit the vertical shifts, which is the VO portion. So V for vertical, O for outside. So this is implying that if it's a vertical shift, it's all going to come from a term that's outside the original function. This is a little different than the beginning portion because we don't have to think of opposites. Notice that in here, we were adding some term, and this implied that we were moving to the left that number of units. Here we were subtracting, it was implying we go to the right. This is where you can kind of go back to your normal motion where if we're adding some term, this is going to be shifting up a number of units. So for something like x squared, if we had x squared plus 1, this would be shifting the original function up 1 unit. So if you know a lot of the points for x squared, if you're just adding on 1 to that, it's shifting everything up 1 unit. Whereas if we're subtracting, that shifts down. So something like x squared minus 2 would shift everything down 2 units. We'll see some reflections. So if we end up taking the negative version of some function, x, this is going to be reflecting across the x-axis. You might have seen this in geometry, reflecting over a certain line. So if we had this function seen here, this is looking like a square root function. If, let's say, it was a negative square root of x, it's as if we would be taking this same line, but now it's going to be moving kind of mirrored over the x-axis. And this is only if we're subtracting the original f of x function. Whereas if we had a negative x term inside the parentheses, this could be reflected over the y-axis like so. We'll also see that some of these functions will shrink or stretch to show that they're moving a little bit quicker. So let's say that if there's some term a that's greater than 1 and it's thrown towards the front of the function, let's compare, well, we stick with x squared. If we now have 3x squared, 3 is considered your coefficient for x squared, and that's definitely greater than 1. So that would imply that it's stretching vertically by that type of factor. So it's moving in a faster format. Let's say that x squared looks like a wider u. 3x squared would definitely be moving in a faster format. So it might look like this in comparison. Whereas if the coefficient is in between 0 and 1, you could think of this as a fraction. So think of this as maybe 1/2, 1/3, 4/5. Think of this as if you were working a fraction of your normal rate. You're working a little bit more laid back. You're not moving as quick as 3x squared was. You might be more relaxed. Let's dash this out. So let's say that it would be more spread out. If we keep this moving with the horizontal stretch and horizontal stretch and compress, this is saying that if the a term, so there's some term inside parentheses, is greater than 1, so it could be 2, could be 3, could be 4, etc. This would compress horizontally by a factor of 1 over a, whereas if the term inside is in between 0 and 1, so a fraction again, like 1/2, 1/7, 1/8, 3/4, this would be stretching horizontally by a factor of 1 over a. So a lot's going on here. There is a lot to remember, but you have this table on hand. We'll see a lot of examples as to how all of this is working, and we'll see what happens in the next video when we graph these out.